Hello, everybody. My name is Masood Olia, and I'm a faculty here at Wentworth University in the School of Engineering. And I'm here again with another video related to the subject of statics and the topic of two-dimensional particle equilibrium. So let's read the problem. It says this block has a mass of 5 kilograms. So remember, if something given in kilograms, you need to convert that to the newtons, which means you multiply the mass by gravity. So here we take the 5 kilograms and multiply it by 9.81. So that would be 49.05 newtons. So that would be the weight of this mass. It says it's resting on a smooth plane, so there's no friction right here. Only the normal force, as we're going to draw the free body diagram in a minute. It says determine the unstretched length of the spring. You see, this is spring, which has a stiffness of 200 newtons per meter. Basically, when you release this, this spring will stretch and will reach the equilibrium position. So it cannot go down any further. So when it reaches the equilibrium, we want to know what is the unstretched length of the spring. So this is really a very simple problem. We need to start actually with drawing the free body diagram here, and then try to find the force of the spring. Once you have the force of the spring, which I'm going to denote it by F sub S, force of a spring, then I should be able to figure out what is the unstretched length of the spring. So let's start with drawing the free body diagram. So basically, this is just a point, free body diagram of a point. I can redraw this for you, but let me just start by saying, okay, the weight of this guy is 49.05. Clearly, there is a normal force, right? Which actually we don't need to determine. And then, of course, the force of the spring, which I put it like this, F sub S. Obviously, this is a stretched, and then the force wants to return back. So actually, the free body diagram, if you want to look at it as a point, I can redraw this here for you as 49.05 as the weight, the normal force as N, and also the force of a spring, which is really what we're looking for. I'll put this as a force of a spring like that. Okay? So as I said, all we need to find force of a spring. Now, for a two-dimensional rigid body, two-dimensional particle equilibrium, basically we have to satisfy two equations. We got to make sure that the resultant force is zero, which means sum of the forces in x and y must be equal to zero. You can't have more than two unknowns, which is the case here. These are the two unknowns, force of a spring and the normal force. All right, but it doesn't mean that the x and y axis is your choice. We don't have to use the x and y axis the conventional way, x being horizontal and y being vertical. You can use it to your advantage. So for example, here, a good choice would be pick your x-axis to be along the incline and y-axis to be perpendicular to that. In other words, in the direction of the normal force. Let me redraw this for you. So if you pick your x-axis and y-axis like that, then basically with one equation, you should be able to figure out F sub S. Since n is in the y direction and we don't need that, we'll just say sum of the forces in x equals 0. We'll pick this to be our positive x-axis. And then we notice that this angle here, obviously, is 45. So that's 45. This is 45. So the question is, what is the component of the 49.05, the weight along along the x-axis? So if you project this along the x-axis, that would be the component, which would be actually cosine 45 or sine 45, since the angle is 45. So, and that's acting in the negative direction, as you could see. Sine or cosine doesn't make any difference in this case. So, and then the question is, what is the projection of F sub S along the x-axis? So you see here, we have this slope of 0.3 to 0.4, which is like 3/4. So since you have this slope here, 3 and 4, this component would be 4/5 of f of s in the positive direction, right? Kind of like saying cosine of this angle here, right? Cosine of this angle. Because you have a 3, 4, 5 triangle, right? Anyways, you can go ahead now and solve for f sub s. And f sub s should be about 43.35 newtons. And since we know for a linear spring, f sub s is equal to k times s, s being the amount of deformation, right? So if I calculate now how much this spring is deformed, right? And let me do that. So s becomes f sub s divided by k. K is given, right? So 43.35 divided by, that's in newtons if you want to carry out the unit, divided by 200 Newton per meters. So these cancel, and what do we get? We get 0.21675 meters. So that's how much this spring has stretched. And remember, the problem wanted to find what? Let's go back up. It says determine the unstretched length of the spring. So look at the length of the spring at this instant, guys. The length of the spring right now is 0.3, 0.4, 0.5. So if the length of the spring, the final length is 0.5, and we know it has a stretch 0.21675 according to our calculation here. So then what was the unstretched length? The unstretched length, if you call it L sub 0, would be the current length, which is half a meter, right? Half a meter here, right? Minus how much it is stretched. And therefore, the initial length of the spring was about, if you round it, about 0.283. Okay, so as always, I appreciate if you like the video and join by subscribing to my channel. I'll be back with more videos near future. Thank you again, and I'll see you soon. Take care.